Okay, so here's the plan for the remainder of the course. There's 3 topics I want to discuss. One is the continuum limit. And this will have discrete harmonic functions converging to smooth harmonic functions as the mesh of the lattice gets smaller and smaller. That's the first instance of the continuum limit. And then the second instance will be the random walks on the lattice converging to Brownian motion. And then the third topic will be, this is also a new kind of continuum limit. And this will be a lattice percolation. And what we will see is that the limiting probabilities of various percolation events are conformally invariant. And Brownian motion is also conformally invariant. And of course, harmonic functions are also conformally invariant. So in some sense, what we're going to finish with are 3 instances where we show that discrete random processes have continuum limits and that the fine features of the lattice wash away in the limit, and that we're left with something that's not just invariant under expansions and rotations, but in dimensions 2, it's invariant under conformal maps. So that will be our last set of examples of this important principle of conformal invariance. And I should say that I may have to do some acceleration or skipping to fit all 3 topics in the last couple of classes, but I'm going to do my best to do some sort of justice to all of them. And whatever I do skip will be in the notes, and whatever is skipped in the notes will be in the syllabus. So there will be resources if you want to dig deeper into any of these topics, all of which are interesting. But my personal preference is to try to do at least one of these very thoroughly. And then, and so I'm going to concentrate on doing this one very thoroughly. That's kind of the prime and classical example. And then we may have to just accelerate a little bit when we do the other 2 cases. Okay, so that's where we're headed. And in preparation for doing, for studying how discrete harmonic functions become smooth ones in the limit, we have needed to develop some deeper understanding of random walks on the integers. And let me remind you what we know so far about random walks on Z. So there's one fundamental thing, which is that the probability that a random walk gets much farther than square root of n steps, the distance square root of n after square root of n steps is small. This is big O of 2 to the minus k for k equals 0, 1, 2, etc. So these tail events are small. This is our weak form of the central limit theorem. And then a couple of other things that were major players in our discussion have been U2n. This is the probability that at the 2nth step of the random walk you return to 0. And this is obviously given by this binomial coefficient, but more to the point, we saw it's asymptotic of 1 over the square root of n up to a constant. And then F2n, which is the probability that not only does this occur, but it's the first time we return to 0. Probability of the first return to 0 is at x2n equals 0. Of course, that will be less than this probability, and it's less by the amount 1 over 2n minus 1. That was an application of the Ballot theorem. And then we introduced these variables t of 1, for example. This is the by definition, it's the least n, such that xn equals 1. Of course, n has to be odd here since we're starting at x equals 0. And it's easy to see that the probability of tau 1 being equal to 2n minus 1 is the same as the probability that your first return to the origin is at time 2n. So let's just think about that for a second. So if you're going to make your first return at the origin at time 2n, you might, for example, take your first step to +1. You either go to +1 or -1. Let's say you go to +1 on your first step. Then to make your first return to the origin at time 2n, you're allowed to go wherever you want up here, but it has to be the first time you cross the line x is equal to 0. So you're starting at x equals 1, and you're looking at the first time you hit x equals 0, and now the total number of steps is 2n minus 1. And that's essentially the definition of tau 1, except we reverse the roles of 0 and 1. X here, xn is equal to 0, and x0 is equal to 0. Here, at time, we call this time 0, we're at 1 at x0, we're waiting to get to 1. Okay, so what I want to do to finish our discussion of random walks on Z is discuss not so much tau 1, but tau m. And so tau m is defined in the same way. It's the least n such that x sub 1 equals m. So sorry for those who are writing notes. And what we're really interested in is the following. If we look at, say, tau 10, let's look at the function, the probability that tau 10 is equal to n. So what we're considering are random walks. Let me draw the random walk over here. They're bouncing around starting at 0, and we're looking at the first moment they finally hit the point 10. And then we look at the distribution of this random variable. This is tau 10, the moment when that happens. Well, first, we expect tau 10 to be roughly 100. A lot of the times it's roughly 100 because within the time, within 100 steps, you should be at distance about square root of 100, i.e. 10 from the origin. And for example, if you were to get up to plus 15, you would have to cross 10 first. So the largest value of tau 10 is roughly around n squared. Tau m is roughly around n squared. So here this was m is equal to 10. This is roughly m squared. But then we can ask, what's the probability that you get there much faster? For example, what's the probability you get to 10 in 9 steps? Well, it's 0. You can't, even if you took all your steps in the right direction, you couldn't get to 10 in 9 steps. Now you could get there in 10 steps, but that would be extremely rare. The probability here would be 2 to the minus 10, because you would have to take all of your 10 steps in the positive direction. So that's almost invisible here. And then what happens is these probabilities go up, and it's very rare that you're more than a couple of standard deviations away. But then once your random walk starts to get up pretty high, then it becomes unlikely that it's taking you a long time to get up to 10. And so these probabilities gradually go down again. And we can guess how they go down because we know how the distribution of F2n behaves. F2n behaves like 1 over n to the 3 halves. And in fact, this tail here is also like 1 over n to the 3 halves, just times a different constant that depends on what n is. Okay, but for our applications, we'll be mostly interested in this regime. We want to show that it's very unlikely to reach distance 10 in significantly less than 100 steps. Okay, so that's the shape, and there's these two regimes to the first crossing time. And with that in mind, let's now just step back and do a little bit of analysis of tau n and of tau 1. Okay, so analysis of tau m reached n, xn equals m. And I always take m to be greater than or equal to 1. Of course, tau minus m is the same. The first thing we can do is we can introduce let's study tau 1 to start out with. And we can introduce the function f of z. This is called the generating function for tau 1. And it's just the expected value of z to the tau 1. So what does that mean? It means it's the sum over n goes from 0 to infinity of the probability tau 1 is equal to n times z to the n. So we can translate the study of all of these probabilities into the study of this nice package where they're all encapsulated at once. Okay, now the second thing to observe is, and we mentioned this last time, is tau m is distributed like the sum of m independent copies of tau 1. In fact, it's good to think of tau m as being the amount of time it takes to go from 0 to m. And to go from 0 to m, you have to first go from 0 to 1. And then you have to go from 1 to 2, all the way out to going from m minus 1 to m. And these variables are independent of one another. And of course, each one is distributed exactly like the variable tau 1. So you break your random walk up to the piece that stops when you first hit 1, then the piece that starts at then and stops when you first hit 2, and so on. And the lengths of all of these pieces add up to tau 0m, and they are independent from one another because they're different parts of the random walk. And now, remember that the generating function for the sum of two random variables is, if they're independent, it's very simple. It's fc times f(a). So what we conclude is that the generating function for tau m is just f of z to the m. There's really only one thing we need to compute, which is the generating function for tau 1. Okay, so that's a beautiful simplification of this analysis if we wanted to go into it in more depth. So that just begs the question, what is f of z? What's the generating function for tau 1? And now here, there's a very beautiful and simple idea, which is that you start at 0, and you're trying to see when you hit m equals 1. And we can break tau m into two pieces. First, there's the possibility that you just hit 1 right off. So there's a 50% chance that tau 1 is equal to 1. On the other hand, your first step might be to minus 1. And if your first step is to minus 1, now how long is it going to take to reach reach m? It's going to take tau 2 steps, because this is the same as walking from 0 to 2. You're starting at minus 1, and you want to know when you're going to first reach m is equal to 2. So really, tau 1 can be expressed in terms of the weighted sum of two scenarios. One where you hit 1 immediately, and one where you have to go distance 2 instead of 1. So what that shows is that f of z is distributed in 2 ways. First, there's a z with a weight of half, and that comes from the probability that you just get there right off. And then there's another term, which is the probability that your first step was to go here. So that's also weighted with minus a half, with a half. And it also gets a z in front, because in both cases, you have to count this first step. And then we put here the distribution for tau 2. The tau 2 has distribution f of z squared. So this very simple argument gives us an algebraic formula that must be satisfied by the generating function. And now you solve this formula using the quadratic equation, and you'll get f of z is, let's see, z plus the square root of 1 minus z squared over z. Let me just check that against my notes. Sorry, it's 1 minus the square root of 1 minus z squared over z. That's just solving the quadratic equation. Yeah. Okay, so now we have a way to analyze tau 1. And also, since tau 1 contains the same information as f2n, this also gives a very nice different route to the computation of the coefficients of f2n. And this function can be easily expanded using the binomial theorem with of course, fractional exponent, 1 minus z squared to the 1/2. Write this out as a power series of z when z is small. So we won't do that, but I just want to allude to the fact that such a method is available to analyze both tau 1 and tau n. But instead, what we're interested in is the probability that tau m is very small. We want to show that that's very unusual to get quite far from the origin in a short amount of time. And for this, we're going to use another formula for tau m, which is based on our favorite method for proving combinatorial formulas, which is what?
Symmetry, story, reflection argument.
Yes, the reflection principle. So the reflection principle is simply that when you have a collection of paths and you perform a reflection and get another collection of paths, the probability of each collection is the same because the cardinality of the number of paths remains the same. So we're going to use the reflection principle to give a formula for this time distribution, tau m, in terms of the space distribution, x of 2n. So I think this is very beautiful. So we're going to relate space and time. And that means we'll be able to use the central limit theorem to discuss time, whereas we usually think of the central limit theorem as being something we use to discuss the distribution of a point in space. So the theorem is that the probability that tau m is equal to n is simply the same as the probability that x of n is equal to m plus twice the probability that x of n is bigger than n. So these are two space distribution questions at a fixed time. And these we can understand very well by what we know already, and this is what we wanted to understand, especially for m large. So here's the proof. So we're interested in the first crossing time, starting at 0, for the line x is equal to m. And we want to know if that we want to know if that happens before, sorry, this should have been less than or equal to, if that happens before time n. So let's suppose tau m is less than or equal to n. So what does that mean about our path? So it means our path definitely has to hit M at some point in time. So let's consider the first point where it hits this line. And then from then on, our path does whatever it wants to do. And it finally is somewhere at time N. So there's three possibilities for its value at time N. It might be less than M, it might be equal to M, or it might be greater than M. Okay, now, so let's just count up the paths that contribute to this probability, to the event that tau m was less than or equal to n. Well, certainly the case where xm is equal to m is included. If you hit m at time n, then certainly you hit it less than or equal to n. So that's included. So we include all of the paths that end here, and that's accounted for by this. Now, suppose your path ends up here, above m. Well, then by the intermediate value theorem, you had to cross m at some point. So that means one copy of these paths has to be included. But now suppose your path hits m, but it ends somewhere less than m. Well, it did hit m at some moment, and so you can take this portion of the path and you can reflect to create a path that canonically create a path that ends bigger than m. And that gives a bijection between the paths that end bigger than m and the ones that end less than m. And so if you put a 2 in here, you've accounted for both. So that explains this formula. Okay, and notice that, of course, this, I wanted to write down something exact, but we can certainly say that this probability is less than or equal to the probability that xn is greater than or equal to m. So here's a corollary, which is the version that I like to use of this theorem. The corollary is that the probability that tau m is less than or equal to, so we expect it to be about m squared. And the probability that it's significantly less than that, let's say less than m squared over k squared, this is, by what we just proved, it's less than or equal to twice the probability that xn is greater than or equal to m. And now what is m in terms of, it's greater than or equal to the probability that xn is greater than or equal to m, where this is n. Okay, now if this is n, then the square root of n is m over k. And so m itself is k times the square root of n. So this is the probability that x of n is greater than or equal to k times the square root of n. So this is the probability that you're more than k standard deviations away from the origin, which is very unlikely. And using our crude bound, this could be made more exact, but we can simply say this is on the order of 2 to the minus k. Okay, so summing up, the probability that you went much faster just by this integral factor of 1 over k squared is exponentially small. So I'm going to erase the proof and just write the final conclusion, which is that this is big O of 2 to the minus k. Okay, so that is the end of the story for random walks in one dimension. And the main thing I think we learned is that the reflection principle is very powerful. That's the first principle we used, and the only other principle we used was that when you write the probability of random walks ending at position I versus I plus 1, if you want to compare those two probabilities, you get a ratio of binomial coefficients, which is just an easily analyzed fraction. That's what we use to prove our weak central limit theorem. Okay, so any questions before we proceed to the continuum limit? I should say you can easily teach a whole course on random walks on the integers, and I really encourage you to look at Feller's book, which has a whole chapter on random walks. That's very elementary, very accessible, and illustrates a lot of surprising things that are not obvious at first sight. But like the Gambler's Ruin discussion that we did talk about. Okay, so on to the continuum limit. Okay, so here's a very simple geometric idea. If you take a sequence of positive numbers decreasing to 0, and you're playing some game that uses the lattice ZD. Well, we can think of ZD as sitting inside of RD, and there's in some sense ZD converges to RD. Now, there's many ways to make this precise. For example, every point in RD is very close to a point in ZD when this mesh size, Hn, is small. You could talk about the Hausdorff topology on closed subsets of RD, then you get convergence in that topology. Perhaps more to the point, though, is if you're doing calculus, calculus involves taking the difference between the values of functions at various points and then taking a limit. And you can do discrete calculus where you take, where Hn is considered epsilon, and then as epsilon goes to 0, the discrete differences should converge to ordinary derivatives. So here, the differences, which always exist, should converge to derivatives, which may or may not exist for functions on RD. So our hope is that maybe not all functions on the discrete lattice converge to smooth functions on RD, but those that are controlled in some way. And one of the most beautiful ways to control a function is via its Laplacian. Harmonic functions are kind of automatically smooth. A function that satisfies the mean value principle on RD is automatically a harmonic function, and then it has derivatives of all order. So our goal will be to show limits of discrete harmonic functions exist, and they are smooth harmonic functions. And the goal is it's interesting conceptually as an example of how this conformally invariant notion emerges from a picture where we've broken all of the conformal symmetry, but it's also of practical importance. So if you wanted in practice to get a good numerical solution to Laplace's equation on a region in the plane, a perfectly reasonable way to do it is to impose a fine grid, place a fine grid over this region. And then approximate the boundary of the region by grid points that are reasonably close to the boundary. Specify the value of your function by its values on the boundary. So in other words, approximate omega by this finite set in the plane with some boundary points, and then solve for the discrete harmonic function on this fine grid and hope that that's a good approximation to your solution on omega. And we will ultimately show that that process works. Now, how do you actually solve Laplace's equation on the grid? Well, we've shown that the harmonic functions, the value of a harmonic function at a point in this discretized grid is just the expected value of its boundary value if you take a random walk and wait till it tries to escape the region. But that's not the right way to compute the value of the harmonic function here. To say the function is harmonic is just to say that it satisfies some big system of linear equations, and the linear equations are sparse, is they only relate a point to its neighboring points. And so the correct way to do this in numerical analysis is by sparse matrix processing. You have to formally invert the Laplacian for the given boundary values, and this can be routinely done and is part of sparse linear algebra. So that's how the solution is actually made. But what we're going to be interested in is showing something that's usually not entertained as a question in numerical analysis, that in fact this approximation is good. And this is an excellent example of where we're going to use random walks to prove that theorem, even though random walks are not used to do the computation. As I mentioned before, solving the Dirichlet problem is an almost trivial linear algebra problem. That's why I gave it very early in the course. But the fact that it can also be solved using random walks gives us a much deeper insight into it and will give us a very conceptual proof of this statement, that discrete harmonic functions become smooth ones in the limit. Okay, so let me try to make that statement precise now. So, I'm going to concentrate on the case equals 2, just because those are the pictures I can easily draw and because we're headed for the complex plane, and it will just put us in a more familiar setting. But the discussion in this section certainly applies to ZD for all D. One of the convenient things here is I can write the integer lattice as just being Z adjoin I, the Gaussian integers sitting inside R2, which I think of as the complex plane. And I should mention that this goal has a very long history. It goes back to 1928 or so in the work of Courant and Friedrichs and Levy. But the proof I'm going to give is very modern. It's in the 21st century by Hugo Duminil-Copin and Stas Smirnov. And not to step on my own punchline, but it's going to use the reflection principle. Okay, so now let's try to formulate it here. So one of the basic theorems about analytic functions on the unit disk is that the set of bounded analytic functions, say bounded by 1, form a compact set. Because when you bound a function by 1, you also bound its derivatives. So the same thing is true for harmonic functions. If you have a harmonic sequence of harmonic functions on the disk bounded by 1, they have convergent subsequences. They're pre-compact. So our first goal, and this is in some sense the main point, is to prove some kind of compactness for harmonic functions on lattices that are getting finer and finer. Okay, so I fix this sequence, Hn going to 0. And then I'm also going to fix this region omega. So omega will just be an open set in C for concreteness. It's 1 over n h Z adjoin I. It's converging to the complex plane, if you like. Okay, and I'm going to let omega n be the intersection of omega with the rescale lattice. So it's defined, it's the red points that you see in this picture. So let Fn from omega n to 0 minus 1, 1 be a sequence bounded discrete harmonic functions. Okay, so as usual, you have to impose some condition like boundedness because you can make sequences of ordinary harmonic functions that go off to infinity. Fn could even be the constant function going off to infinity. But we're going to require they're bounded, and then we'll obtain compactness. And in particular, we'll show that Fn has to converge itself to a harmonic function, at least after passing to a subsequence. So then, after passing to a subsequence, there exists an ordinary smooth harmonic function. Let me call it capital F from omega into R, such that, well, I want to say that Fn tends to F, we first write it conceptually, uniformly on compact sets. Now, what does that mean, really? There's two possible ways to make this precise. So the first would be the following. If we fix a compact set inside of omega, then the sup over k intersect omega n of the absolute value of Fn of z and Sf of z tends to 0. So I compare the functions where I'm allowed to compare them, and then take the limit. The second way to do this is, and this is also common. I bring it up primarily because it's a convention you'll see very frequently. The second way to do this is you take your square grid, HNC adjoin I, and you triangulate it. That is, you add more edges to cut it into triangles. They add the diagonals of all of the squares. And now, if you know the values of F at the 3 vertices of a square, then there's a unique way to extend F so that it's linear in this square. And so what we can do is, as we're going along, instead of thinking of Fn as a function on just this discrete set of points, we can think of it as a function on all the squares that are contained inside of omega. And then we can take this set of the union of these squares eventually fills omega. And so, and then the function is defined everywhere. And so then this statement makes perfect sense from that perspective as well. And I bring this up partly to mention that another way people think about solving the Dirichlet problem in terms of linear algebra is they say, instead of looking at harmonic functions F or smooth functions F, I'm going to look at functions that are PL. They're linear on each of these triangles. And then when you have a function that's linear on this triangle, you can attach to it the gradient of F squared, just by taking the gradient of that linear function. Then you can add that up over all the triangles, ask that you're at a critical point, and you'll again be led to a set of linear equations to solve. And one reason that that formulation is so useful is that it doesn't have anything to do with this being a square grid. So you could also take your region and you could triangulate it in any way you want. And you might want, for example, that near some points there are lots of triangles because you're afraid your function is going to be very changing very rapidly there. You use big triangles in the regions where you think the function is going to be nearly constant. And you might want to adapt your triangulation so it follows the boundary of your region better, rather than having this kind of step function cutoff that you would get with a square grid. And one can pursue everything that we're talking about today in this more general setting. This is what's called the finite element method. Each of these triangles is called a finite element. You can use simplices to do this in R3, and it's actually used in practice like that in industry. Okay, so that's the statement of the theorem, that it's saying that discrete harmonic functions look more and more like smooth ones. And we will eventually make that into a very precise statement that will even give a sort of rate of convergence. Okay. So now we come to the heart of the proof. And the heart of the proof will be phrased by not in terms of this limiting thing, but in terms of random walks on the ordinary lattice. And then by rescaling, it will give us what we want in the general lattice. So here's our first goal, is to prove that the following: let f of z be harmonic on the square minus n cross minus n in z adjoint I, and bounded by 1. Then the absolute value of f of I minus f of minus I is less than or equal to 1 over n with a constant thrown in. C is going to be a universal constant. Okay, now let's think about what this is really saying. So we have this huge region, this huge square centered near the origin, and we look at the value of f down here, and we look at the value up here. And the claim is these two values are close together. How close are they together? Well, the main thing is that f is bounded by 1. So what we're hoping is that when f is bounded by 1, that the function varies very slowly throughout this large region. And so what we expect is that the derivative of f should be bounded by something like 1 over n in the middle of the region. That's because if we scale everything down, that will say that the derivative of f, the ordinary derivative is bounded by 1 on a square of radius 1 with a very fine mesh. Okay, so the main point is that here we have this function that's fluctuating up and down by 1. For example, you might imagine it's 1 here, it's 0 here, it's doing something wild here, but always bounded by 1. But then when you make it harmonic, all of this stuff kind of smooths out in the middle, and the function does not vary very much more than it has to in the middle. After all, it might need to go from 0 to 1 on the two boundaries, but it doesn't have to do that by changing by more than, say, 1 over n as you pass between two adjacent sites. And so this says that the variation of f over two nearby sites is just about as small as it could possibly be. And that fits with our idea that harmonic functions sort of minimize energy. They give the best possible extension of the function. Okay, so that's our goal. But actually, that was just a bit of a feint, a red herring. So, of course, this is also our goal. This is gone now. This will be an estimate that's sufficient to prove the compactness in the end. That's not hard to see because it's like controlling the derivatives of f. But there's an intermediate goal, which is actually our main goal. And it's not at all yet obvious why this goal is so important. But here's the theorem. It's in the same setting, and the statement is about random walks. And it's a somewhat subtle theorem, and it's maybe a little delicate to guess, And it's not trivial to prove. So the theorem is, again, let F be discrete harmonic on the 2n by 2n square. Sorry, this is not what I want to say. F is gone now. Consider a random walk on z adjoint I, starting with z of 0 is equal to I. So I should say that when I do random walks in C, I'm going to write the random walk as Zn is xn plus I times yn. And remember, each of these coordinates, only one coordinate changes at a time. We choose one of the two coordinates and then we move it up or down by one with equal probability. And so these individual coordinates undergo random walks with posits because x doesn't change while y is changing. Otherwise, they're doing ordinary random walks. So we consider a random walk starting at not at the origin, but at the point right next to the origin, I. So here's our lattice. And again, we're going to be in a big square. Then the probability that z of n exits the 2n by 2n square before it crosses the real axis is big O of 1 over n. So we start doing our random walk up here. Here's the real axis. And now we might do a random walk that goes like this. It stays entirely in the upper half plane, and then it finally hits the boundary of the square. And when it does so, it might hit it at the top edge, or it might hit it at the side edge. But that should look weird to you. What's much more common for a random walk in the plane to do would be for it to start to spiral around the origin and cross the real axis many times before it exits the square. It's a little bit perverse for it to stay entirely in the upper half plane. And what we need is a concrete estimate on the probability that this happens, and it turns out the probability will be on the order of 1 over n. Okay, so I haven't explained how we're going to use that, but it's going to be the key to the proving this theorem. So let's do the proof of this crossing. Let's study this crossing probability. Okay, so the proof. So let tau be the least n such that xn is equal to capital N, or yn is equal to capital N. So it's the first moment you leave the square, S. Okay, now there's two cases. The first case is if it's y of tau is equal to n. Oh, and so we suppose, by the way, let's suppose that z of n never crosses the real axis. Our estimates will all be contingent on this assumption. So suppose we don't cross the real axis, and we look at the first moment that we do escape the square. So in fact, y of tau is equal to n. It can't go into the lower half plane. Okay, so this is the case where we started at I, and we hit this line here. Okay, now let's just think about the random walk y itself. So y at time 0 was equal to 1. Its imaginary part of z is equal to 1. And what's happening is that y is doing a random walk with pauses on the integers. And it's hitting the point n before it hits the point 0. Now, the distribution properties of a random walk with pauses are the same as the distribution properties of a random walk without pauses. You just throw the pauses away and you're left with an ordinary random walk. And the outcome, the probability of this event is the same once we've eliminated the pauses. So we just have to ask, what's the probability that a random walk on the interval 0n, starting at 1, exits at n instead of 0? And that's something we know very well. In fact, the probability starting at k that you exit at n rather than 0 is k over n. It's a harmonic function. So the probability that starting here, you exit way over at n instead of right next to you at 0 is 1 over n. Okay, so this probability is equal to 1 over n. Okay, so we've divided the event that we're trying to control into different cases. And in one case, the probability is certainly less than or equal to 1 over n, because I've conditioned on something like some special event happening, and then subject to that conditioning, it's still less than or equal to 1 over n. Okay, so that's good. That supports the theorem. We just have to deal with the remaining cases. So the remaining case is that x sub tau is equal to n. And so now we have something a little bit different. So we have the in absolute value. So we have minus nn, and now the random walk in the x direction is going faster somehow than the random walk in the y direction, and we're exiting on one of these two sides. And we're still interested in controlling what happens with y, because y is what determines whether or not we stayed in the upper half plane. But it's x that's exiting the region. So we have to somehow take information about x and turn it into control of y. Okay, so now I'm just going to quote a fact which is easily verified, which is that with very high probability, the number of y steps is greater than or equal to tau over 3. And when I say with very high probability, I mean like one much, so much better than 1 minus 1 over n. So if we neglect an extremely unlikely event, then the number of y steps and the number of x steps is almost exactly the same. Remember, this is like saying you flip a coin 1,000 times, you want to show it comes up heads at least 300 times. To come up heads fewer than 300 times is a huge number of standard deviations. And so that event is extremely unlikely. We bounded that when we proved the strong law of large numbers last time. So I'll just assume that general principle, that when we do a random walk in many dimensions, you take about the same number of steps in every direction within a small multiplicative error. Okay, so y is doing about tau steps as well. So now comes the key question is, what is tau? What do we expect tau to be? So let's do a couple of scenarios. So we expect tau to be, well, let's see, we have to reach distance n in a random walk starting at 0. So we expect tau to be greater than or equal to n squared a fair amount of the time. So let's suppose that tau is greater than or equal to n squared. And now let's see what has to happen for y. Then what y has to do is y has to do a random walk starting at 1, and it has to never reach 0. So that's exactly the probability that tau of 1 is that's exactly like the probability of tau of 1. Sorry, the probability that the first return to the origin takes more than tau steps. So the probability that yi is not 0 for I equals 1, 2 to tau is like the probability of no return to 0 at all up until time tau. And we've seen that this is approximately 1 over the square root of tau. And now if tau is greater than or equal to n squared, this is less than or equal to 1 over n. And so we're done in that case as well. As long as x is giving y a long time to hit the origin, then it's quite unlikely that y doesn't do that. If you wait long enough, y is definitely going to hit the origin because random walks on the line are recurrent. So that also works. But now there is one problem, which is what if x goes really fast? What if x reaches one of these boundaries not in time n squared, but in time much less than n squared? Well, so now suppose that tau is comparable not to n squared, but to n squared over k squared for some integer k. In other words, we'll divide it up into cases where this is approximately the size of tau instead of tau being bigger than n squared. Now the probability of this happening is, as we just estimated, this is the probability that that tau of 1, this probability is so this is the probability that tau of a certain m, the m being n itself, is less than or equal to n squared over k squared. So it's less than or equal to this. And the probability that this happened, as we just saw, is big O of 2 to the minus k. So we do have to consider the events where x moves rapidly, but these have exponentially decaying probability. And then given that tau is on the order of n squared over k squared, the probability that y of I is not equal to 0, for I goes from 1 up to tau, is still on the order of 1 over the square root of tau, which is now on the order of k over n. So the probability that y never hits the origin is going up. That's the scary thing. If you have less time to cross the real axis, it's more likely you don't. But the probability you have less time is going down. So the total contribution comes from the product of these two. So it's the sum of 2 to the minus k, which is the probability that the escape time is on the order of n squared over k squared, times the probability that y doesn't hit 0, which is going up, but it's like k over n. Well, the sum of 2 to the minus k times k converges. This exponential easily swamps out the effect of this growing k here, and so this whole thing is on the order of 1 over n as well. Okay, so that is the main technical lemma in the proof of this theorem. It's that with a definite bound, it's much more likely, it's very likely that if you're going to escape from this box, you're going to cross the real axis at some time. Only about 1 over n of the time can you escape while staying in the upper half plane. I think this is the most intricate proof that we do in this class. So I wanted to do one proof that gets to the heart of the matter in complete detail. And that's why we did all this preparation on random walks on the integers. Interestingly, when you're studying random walks in the plane, it can be very useful to understand in detail random walks on the line. Okay, so now comes what was stated as the goal, which is the theorem that says if we have f mapping minus n squared, we'll set c join I into R into minus 1, 1, harmonic, then the absolute value of f of I minus f of minus I is less than or equal to a constant over n. It's very smooth out of the middle. Okay. So here's our big square. This is supposed to be n on the side. And we have I minus I. These are the two sites we're interested in comparing. And we have our function f, which is harmonic. And so we can write the value of f at I in terms of the value of f on the boundary of this square S. So for the proof, we observe that f of I is just the expected value of f at x of tau, z of tau. Now let's write parentheses here, where z of 0 is equal to I, and tau is the first moment z is in the boundary of the square. And in fact, the same thing is true for minus I. So I'm going to put it's a plus or minus in here, and then I'll have a random walk that changes depending on where you start. So z of 0 is plus or minus I. And then we have tau plus or minus. It's the first moment where z plus or minus reaches the boundary. So we have expressed both of these probabilities in terms of the expected values of f at certain points along random walks. And these random walks differ only in their starting point. Okay, now here's the beautiful idea. Every random walk z plus can be matched to a random walk z minus. In other words, there is a measure preserving bijection between the random walks that start at I and the random walks that start at minus I. It preserves probabilities, and it has the property such, and it will have the property that such that z plus of I is actually equal to z minus of I, where for all I greater than or equal to some value s. And what is the value s going to be? S is going to be, actually, let me call this sigma. It's going to be the first moment z plus hits the real axis. Okay, so this is our reflection argument coming in, and let's see how it works. So forget about the square for the moment. We're just doing a random walk in the plane. Now the y-coordinate of the random walk is doing a random walk on the line. It's recurrent. So eventually it hits the real axis. So we start doing this random walk, and at some point, we hit the real axis for the first time. And now what do we match that to? Well, we just take this path and we reflect it through the real axis. And now we've paired it to a path z minus that starts at minus I. And now what happens after that? Well, you just let them do the same thing. So you take z plus and you pair it to the path at z minus that's identical to it past this moment s when it hits the real axis. And obviously, if we were to start with this path, wait till the first moment it hits the real axis and then flip over, we would get the path c plus. Sorry, this is called sigma now, to make it look more like a stopping time. So I should have said this is Z plus of sigma, which is equal to Z minus of sigma. Okay, now, that almost proves that these two quantities are the same. Because you see, if these paths are, if the path doesn't depend on whether you put a plus or minus sign in here, then the expected value of f is the same. And so we've almost proved they're the same. Well, what have we proved? What we have proved is that the expected value of f plus of tau equals, subject to the condition that sigma is less than or equal to tau, is equal to the expected value of f of z minus of tau, subject to the condition that sigma is less than or equal. Sigma minus is less than or equal. This should be sigma plus and sigma minus, less than or equal to tau minus. In other words, if we throw away the paths that fail to meet the real axis, then we get equality. But we have introduced an error. And the error is we forgot to add up, when forming this expectation, the paths that do this weird thing where they stay entirely in the upper half plane before they exit. However, the probability that you have a path where sigma is greater than tau is big O 1 over n. So this is a rare event. And for those rare events, we're counting up the values of f, and the value of f is bounded by 1. So when we form the expectation, we get what we would get by just neglecting these paths entirely by introducing an error of size 1 over n. And that's the proof of the theorem. Okay, so f does not vary very much when you change from I to minus I. Think how painful it would be to try to prove this theorem without using random walks. So once you're set up, the proof is very simple, and you see what you have to estimate very clearly, just that you frequently cross the real axis so that you can use the reflection principle. Okay. Now, there's a little bit of there's a little nuance which I hope is bothering you at this point, which is I'm now going to assert that the values of f vary slowly as you move around inside of this square. I've proved that it's true if you compare I to minus I. Clearly, I could rotate it, and it would be true if you could compare +1 to -1. But what's wrong with this theorem as stated? What points are hard to compare?
Points at distance 1 from each other?
Yeah, this gives us no information on how the value of f at I compares to the value of f at 0. You see, what it says is if you change your location by 2i, then the value of f changes by this small amount. If you change your location by plus or minus 1, in other words, by 2 in the horizontal direction, it changes by a small amount. So in fact, as a corollary, this shows that the absolute value of f of z minus f of w is less than or equal to a constant times the absolute value of z minus w over n if, say, the absolute value of z minus w is less than or equal to 1/2 n. Sorry, absolute, if we're well within the square so that we get this bound to hold. And the difference, z minus w, is in 2 times z adjoint I. So in other words, it takes the lattice where we're trying to control f, and it breaks it up into some sublattices, which are the cosets of z adjoint I. So what we know is that f is almost constant on this sublattice. And then we also know that it's almost constant on this sublattice, where I'm putting in x's. And then we also know it's almost constant on this sublattice. So I'll put in dashes. And it's also almost constant on the sublattice of the dots. But it doesn't say it's almost constant on the whole lattice, at least not yet. Okay, but this is a very easy issue to fix. So what we did was we made this theorem very easy to prove, and then after the fact, we have to fix things up a little bit here. But the point is very simple. What is the value of f at this red point? It's the average of the values of the dashes and the average of and the values at the pluses. So f is approximately constant here. It assumes 4 different values to within an error of 1 over n. And those 4 values are the same on the pluses and the minuses and the circles. But on the circles, it's equal to the average of the values on the pluses and on the crosses and the dashes. And on the dash, it's equal to the average of the values of the circles and the dots. So it's assuming 4 values which are almost the same. And then because of the fact that it's harmonic, those 4 values themselves must agree to within an error of 1 over n. Another way to put this is, suppose f was actually constant on each of these lattices. Then f would descend to a harmonic function on the lattice zi mod 2i zi, which is a compact space, and by the maximum principle, it would be constant. Or to put it differently, if f were constant on each of these sublattices, it would assume its maximum at one of them, say at this point m, but then the value here is the average of these nearby values, so it would have to be maximum, assume the same maximum on every coset. So there's a little argument to that effect, and what it allows us to do is to just erase this assumption that the difference lies in the sublattice. Okay, so this is pretty good. Okay, so now let's go back to our region omega. And let's suppose that 0 is in our region, and suppose even that the unit disk is in our region. And now we have our lattices Hn Z adjoin R. So we focus our attention on one of these. And this intersected with omega is this lattice omega n. So if we take omega n, intersect the unit disk, what do we see? Well, we see gaps that are on the order of Hn. And how big a square can we draw inside of this disk? Well, we can draw a square whose side is about n is comparable to 1 over Hn. So remember that we proved now that for adjacent sites, if you take f of z plus Hn, for example, minus f of z, that's like taking 2 adjacent sites in the lattice. We're assuming that f is less than or equal to 1 here on omega, and f is a bounded harmonic function. And now we've been able to inscribe around this point z a large disk, a large square, I should say, of size n. And so by the bound we just proved, this difference here is less than or equal to a constant times 1 over n. But 1 over n is comparable to Hn. So this is less than or equal to a constant times Hn, or to put it differently, this ratio divided by Hn is less than or equal to a constant. Okay, so what that shows is that if you focus attention on, say, a unit disk contained in our region omega, then the derivative of the function, the combinatorial derivative, is bounded within that disk. In other words, the function looks more and more like a discrete approximation to a Lipschitz function. Another way to put this is that if you take the PL extensions of these functions, then they are genuine Lipschitz functions on the disk with a bounded constant. And of course, the functions Fn are bounded by 1. So let's return to our theorem, which was that Fn restricted to omega n converges after passing to a subsequence to some f from omega to r harmonic. So the proof, the first step is to observe that on any compact set, okay, contained in omega, the Fn are uniformly Lipschitz. That means that this inequality holds with a constant that that doesn't depend on z, but it only depends on the compact set. And of course, once they're uniformly Lipschitz in this sense, that is, as I move one lattice point away and divide by h, it also follows that f of z minus f of w is just straight out less than or equal to some constant, depending on k, times z minus w. Whatever lattice points we pick in this region. And so, by the Arzela-Ascoli theorem, there exists a uniformly convergent sequence. Okay, so we already have made huge progress. We have these functions which are bounded by 1. Now, their Lipschitz constants are bounded, at least uniformly on compact sets, and they converge uniformly on compact sets to some continuous limit. That is a big step up. But it's far short of proving that f is harmonic, because a harmonic function is going to have derivatives of all orders. So maybe we should think about whether or not we can prove that these functions are harmonic. So what we do next is we define dx of Fn to be approximation to the derivative of f in the x direction. So how will this be defined? We'll take Fn at a lattice point, sorry, I should call this z plus hn minus Fn of z, and divide by hn, just as we did before. Now, what we have so far from what we've observed is that the absolute value of dx of Fn is less than or equal to a constant. That's pretty good, but we certainly don't want these functions to be fluctuating all over the place. It's good that they're bounded, but we need more control. There's something magical, though, about this function that we can exploit. Just remarkable, amazing property when we take the combinatorial derivative of a harmonic function. What can we say about the result? So let's think about analytic. Oh, I'm sorry, I'm way over. I'm just getting in the spirit of the argument. We're almost done. Okay, so maybe let me just finish by making this point. If you take an analytic function and you differentiate with respect to z, it's still analytic. What happens if you take a harmonic function and you differentiate with respect to x?
It's still harmonic.
It's still harmonic, right? Because the Laplacian commutes with differentiation by x. They're just linear differential operators. So this function is combinatorially harmonic. This function is combinatorially harmonic. being harmonic is invariant under shifting. And so this guy is also harmonic. Okay, so to make a long story short, this function is bounded by our previous discussion. Even better, it's still harmonic. And so since this is harmonic, this function is also Lipschitz. And therefore it converges to some, after passing to a subsequence, to some other continuous function g. Then we show g is equal to df dx. And just keep going like this. We can differentiate any number of times in any number of directions. The upshot is that f is in fact smooth, and then the fact that AFN is equal to 0 implies that the Laplacian of f is also equal to 0, and therefore we have a harmonic limit. Okay, so I'll recapitulate the end of the argument next time, and then go on to applications. Thanks for your patience. Next time, yell when it hits 120.